Hello, my name is Kareem, and I'm going to be presenting my sorting assignment. I decided to go for the tree sort, and I'm going to be comparing that to the bubble sort. So, one, we have a few options here. We have, one, two, and three. So let's input one. So to start, we have 10 indexes here, 10 values indexed in the array, and they're not sorted here. And then we do the bubble sort, and then we input the time. We can see here it's 0, 1, 2, 4, 4, 4, 4, 7, 8, and 8, and 9. It's sorted here, and our time is 4 thousandths or 46 thousandths if you so choose. And then, we can do this a few more times. We get 51 thousandths, and then we get, 4 thousandths. Now, we can use tree sort, and tree sort, we're looking at 5 thousandths, 6 thousandths, and 7 thousandths. So it did noticeably worse compared to bubble sort. But now what we're going to do is we're going to set the value to 100. I'm going to go a little bit faster this time because you get the basic concept of how the code works. So one bubble sort, we have 100 indexes here and 100 indexes sorted here. And we're looking at 600ths, 500ths, basically 600ths, and then 500ths, basically 600ths. And then tree sort. Now we're looking at basically 700ths, 700ths, 700ths. So it did a little bit worse, not significantly worse, but it definitely didn't wow me in performance wise. So now what we're going to do is we're going to get the size of array using 1000. So it's going to be 1,000 size array, and it's not going to output it, but we are going to get the time. So we're going to do bubble sort, and we're looking at 200ths. Let's do tree sort. We're going to do that a few more times. So we're looking at 2, 3. Well, basically 2. We're looking at 2 hundredths of a second. Now, if we do tree sort here, we're looking at it's not even not even a hundredths. It is basically 4 thousandths, and then we're looking at 3 thousandths, and then 3 thousandths again. So it kind of blows out the water when we're using a really high number for the array size. Which I guess the key takeaway here is that bubble sort, kind of has a variety in its size, but generally when we're looking at really big indexes, it seems to really struggle. In smaller indexes, it does okay. And then for tree sort, when we're looking at smaller indexes, it does okay. But for really big indexes, it seems to perform exceptional. So my code is pretty simple here. We have a few values for clock t, which basically is just me controlling the start and end time. So we know when we started the array and when we end the array. The constant size of the array, this is just so that I don't have to go throughout the code and update the number everywhere. I can just use size of array to define, when we're randomizing things, when we're comparing them, when we're using functions, so on. So, and index nums is just the array that we use and update. Surrounding simulation is just the main while loop boolean, which we toggle when we're done with the program. And then user choice is just the input from the user, as we can see here. If the user choice is equal to 1, then we're going to loop through the size of the array. So in this case, it would be 1,000. So we're going to do this 1,000 times. For every index of I, we're going to set that value equal to a random number with respect to the size of the array value, which in this case is 1,000. So basically, it's not going to be a number that is greater than 1,000, but it is going to pick a value from 0 to 1,000. And then we're basically going to get the size of that array by doing the size of the array divided by the size of the array at index 0, which is us basically just getting us dividing the bit size to figure out how big are we talking about for an array. And if there's 1,000, I believe if this is for, yeah, if there's 100 items, it would be like, I think 4 is an int. I might be wrong about that. I think 4 is an int, so this would be 4. And then if there's 100, then this would be 400 bits. 400 divided by 4, 100. I believe it works something like that. If that value is equal to or less than 100, then we're going to print every item in the array. Otherwise, we're not going to print it. That's why it didn't work for 1,000. And here what we're doing is we're basically starting the clock. The high, we have auto start high, which was the decimal clock, just for a more specific clock that gives us the decimal points, a more accurate time to compare to. And then you have start clock, which is just the normal clock, rounded. Then we do the bubble sort, and then we end the clocks. That we do the end clock, and when we end the, the high quality specific clock or whatever. And then we calculate the difference by doing the end time minus the start time and printing out those values. We do the exact same thing for user choice 2, because we do the same thing, except we just run the sort tree function after we do start clock. And then user choice 3 ends the code, and anything else just doesn't work. Here are my headers. Swap bubble, sort tree. And I'm going to cover swap bubble first, and then I'll cover swap tree. I accidentally ended the recording, but for swap bubble, what we have here, no, I'm not going to cover that. I'll start with sort bubble first. So sort bubble, it requires us to return the array and then the size of the array, which is n. We create two values, which is called int I and int j. Which basically we're going to be doing a loop inside of a loop. So for as long as I is 1 less than n, which is the size of the array, so 1 less than the max of the max of the array, what we're going to do is we're going to we'll do this other loop, which is going to run as long as j is less than n minus 1 less than I. And the reason why we do this I minus 1 is specifically because we want we're never going to reach that value. Since we're going 1 less than the maximum value, which is n, we would never reach this, so it's just pointless to even have it go to that value, or have the chance to go to that value, because it's never going to reach it. And then what we do inside the loop is this: if the value at array index j is greater than the value that is next, then we're going to swap those two values. And what we do is we send the address of that value and the address of that next value to the swap bubble function. And inside the swap bubble function, what we do is we essentially take those values and we store them. So we store the x value, we store the value, this j value, inside the x pointer, and we set that value equal to our int temp. Then we set our x pointer value equal to the y pointer value, which was this value, j plus 1. And then we set that value, this y pointer value, equal to the value that we stored within temp. So now basically x equals y and y equals x. And then we are just going to rinse and repeat that. So then it would keep going until like if we're doing, let's say 1,000, then it would be like, if I is equal to 0, then what is this, 1,000? It would have to, I think it would reach like 999, and then we would loop again, and then we would loop again, loop again, so on and so forth until we reached 999, and then it would stop. Now, as for the tree sort uses binary search trees, otherwise known as BSTs. I got this code from Geeks for Geeks. I did minor tweaks to it, added my own comments for the most part. So yeah, I'm just gonna kind of explain this to my best ability. So we're gonna start off with sort tree. Now, sort tree requires the same stuff that we did for the sort bubble. All we need is the array and the size of the array, which is n. We're going to first create a node, a structure, which we use node root is what we're going to call it. We call it root, and we set that value to equal to null. The first thing we do is we set that root value equal to insert root and array index 0. So we're going to run this function now, right? So array index 0 is key, right? And root is our node. If node or root is equal to null, which if you remember it is going to be null, then we're going to return new node key. So essentially what we're doing is we're setting root equal to that first index in the array. And then that's it. That's it for this function for now. But after we do that, we then have this loop. And essentially this loop is going to run until we reach the size of the array. Until we reach the size of the array. So for every index of I, we're going to set root equal to insert root array index I. And now with insert, what we're going to be doing is this. Basically, if the tree isn't empty, which it won't be since we inserted a value, which was 0, if the key value, which would be array at index I, if that value is less than or equal to the node.key value, right? So the value that we're currently looking at, then we are going to set the value to the left side of it, the root dot left's value. We're going to set that, insert that value. We're going to set that value equal to insert root dot left key. So essentially, basically comparing it to the value that's on its left side, and we're going to compare that value to its left side, and we're going to compare that value to its left side, so on, so on, so on, until we reach node equals null, in which case we're going to return that value, and it's going to be set to that value. So basically, is 8 less than 7? No. Okay, so now that value is equal to 8. And then otherwise, if the value is, if the key value, the value at array index I is greater than the root.key value, then we are going to do the same thing basically, but for the right side. We're going to set the value for the node.right equal to insert node.right key. So is 8 greater than 9? No. Okay, set that value equal to 8. And if there isn't a value, then we're just going to return that value. So it would be 8 equals 8, or that value equals 8. But yeah, we're just going to keep doing that. We're going to keep doing that, keep doing that, keep doing that until we've done that for the size of the array. And then after that's done, after that's done, we are going to be doing this. We're going to sort that array, starting off by setting I equal to 0. Then we're going to return the values, the node root, the array, and the I value. And what we're going to do is check first, is root equal to null, right? If root is not equal to null, this means that we have not reached the end of whatever we're looking at. And I'll explain this a bit more in a second. But basically, if the value we're looking at exists, or the node we're looking at exists, I should say, then we're going to run this function again with the left with the value to the left of this node. And then we're going to, this is going to basically just be a continuous, this is going to loop itself basically. So it's going to keep going until we reach the very end where it's like, okay, there's no more values on this left side. So what we're going to do is set array. Well, so what we're going to do is just, we're not going to run this function anymore. It's not going to, it would just stop there, right? It would just return. But keep in mind, every single time it runs this function and it passes this check here, it's going to be doing this. So it's going to store the current value of the node inside the current index. And what that means is we're just going to set the value in the array equal to the value that we're currently looking at, which would be root.key. And then what we're going to do is increase I. So we're going to check the next value, right? And we're going to, sorry, that's my, if you can hear my brother, it's my brother in the background laughing. But we're going to set the next value, the value to the right. We're going to check that value. And we're going to check that value, check that value, check that value. And we're going to basically run this function again and again until we reach a value that doesn't exist, right? And then it would just return and it wouldn't go through anymore. Essentially what we're doing here is we're just checking to see, okay, does this value, we're going to check, does this value exist on the left side? Okay, update the middle value. All right, check the right value. And it will repeat that, repeat that, repeat that until it reaches the endpoint, and so on for every index in the array. And then after all of that is done, we are going to check if n is less than equal to 100, then we are going to check all those values by just outputting them for every index of I. We're going to output every value using I. So yeah, that's how the code works. I'm not sure if I explained that well. It was kind of difficult for me to explain it. The main thing that the code is basically verbatim for Geeks for Geeks. Oh my God, Geeks for Geeks. But they were under the assumption that the code itself, like I mean the array itself, wouldn't have repeating values. Like when I did, like if it was like multiple zeros or something like that, it wouldn't update it properly. So that I added where is it? It's an insert, isn't it? Yeah. I added less than equal to and that made it work properly, because it was working, but it just only did it for like non-repeating values. But yeah, thank you for listening. I know I went on for a long time, so I'm sorry about that.